And we were here yesterday, we were seeing some calculation of how to find out the volume or the number of moles, and then number of moles back to the mass or weight of a compound in a chemical reaction. And we have seen it yesterday. So if you have any question, of course, you can bring forward. And today we are going to learn the second part of it, that the ionic reaction. We have seen about the molecular reaction, these different type of reactions, and those all the different type of reaction that we have seen before are also applied here, but only this time when we are going to look at the reaction in ion from the ionic perspective point of view, we will try to see what type of ions are, or what is the charges, or how much of the ions are involved in this type of reaction. And surprisingly, we'll see that by looking at the reaction through the ionic lens, we can also justify the precipitation reaction, and of course the acid-base reaction, double displacement reaction that we have seen before, and more interestingly, that the redox reaction. Okay, the redox reaction, how we can explain the redox reaction as well. We will be looking through it, and afterwards the gravimetric analysis. Okay, the gravimetric analysis, we'll see. The gravimetric analysis is one is a quantitative method. We will talk later on. But before, let me go very quickly. I am sure that most of you are aware of it, but just to refresh. Solute, solvent, and solution, these three terms we frequently use in our discussion. The solution is the mixture of all those things that we know. Is very convenient for us, and many students I have seen before that solution is okay for them. But solute and solvent, mostly they will be confused with solute, the solvent. Solute is the matter that has been in the solution in a smallest quantity that will be dissolved in a bigger amount of other thing, that is the solute. And that bigger amount, comparatively bigger amount of other thing is the solvent that is used to dissolve. So solvent will dissolve something and solute will get dissolved into the solution. So altogether, these two solute plus solvent will produce a solution. And there are different types of solution as well. Not necessarily it is in a liquid form. It can be in solid and gaseous form as well. So in liquid form, that sugar water, that or salt water, this is a solution. This is a good example of solution. And in that case, salt is the solute and water is the solvent, and the name of the solution is salt water, right? So so for this case, we see that air in gaseous phase, air is a mixture of many things, isn't it? Of many. We have oxygen, we have carbon dioxide, we have so many particles and dust, and everything is air. So this air is a mixture of many things, right? These many things are the solute inside, and the gas that has the maximum amount of the gas. Nitrogen by far is the maximum, 78% nitrogen in the air, we know. So nitrogen is the solvent, and solute is the small particle. Oxygen, hydrogen, argon, or even particles, carbon dioxide, all those things are solute. All right, so this is air, and we have seen liquid. And for solid, brass or other metal amalgam that we produce, the amalgams, metal amalgams, those are the solution. So brass is not a single metal, it's a mix of different metals. For example, zinc and copper. copper in more, little bit of zinc is used. So brass is very shiny, golden color. Sometimes it is confused with the gold. So brass is produced in this way. Copper, however, is not golden color, it's a reddish color, right? Reddish, something ruby reddish color. Zinc is also a whitish color, but they make the brass golden color, and this is an alloy. And the same way we can also consider steel is an example of solution, because in steel we use iron and nickel. Iron, of course, the most amount, and nickel and magnesium and all those things, titanium, depends on the usage of this iron. Many other things are used. So iron is a solid alloy, and it can be a type of solution as well. So gas liquid interface can be used as well, that when gas is dissolved in water, this is not a solution. I mean, this is not a liquid or solid, but it is a aqueous, or sometimes we can say that sol gel type of solution. All right. Probably we'll see later more about it. But the question is now that how does this, some of the particles get dissolved in water and some doesn't, even though they are the same, similar appearance, similar looks similar very much. So why some of them does get dissolved and some of not? For example, sodium chloride, you can go to this YouTube channel, and then it is nicely and elaborately explained. I'm going to very quickly here that this sodium chloride, for the dissociation of sodium chloride is sodium positive ion and chlorine negative ion. All right. So when it is in the water itself, we have seen yesterday, we were talking, the water is itself a polar compound. It's a polar solvent, right? This is delta positive, negative charge, this is delta positive. So there is a tension between hydrogen and oxygen. And same goes for this one. This is also positive charge. So there is a tension between this hydrogen and oxygen, and so on. And there is, of course, this is a polar covalent bond. So here, like dissolves like, and this water will try to get a hold on this negative charge, chlorine negative charge, and this oxygen will try to get hold of this sodium charge, and that is how they will come between them. It is not totally separate bond, like sodium and chloride is totally separated and there is not sodium chloride anymore, not like that, but it is, there are sodium here as well. Okay, there is sodium as well here, and with this sodium molecule cation, the more oxygen of the water is nearby. It is surrounding, the oxygen here is surrounding this sodium. So both of them, sodium and chlorine, they have different audiences, right? Different depends on their audience's interest. They have different, for example, chlorine is surrounded by water, but hydrogen is surrounding mostly the chlorine, and the sodium is surrounded by water as well, but oxygen is surrounding this sodium. But this sodium and chloride are still they are still in the same bond. They are still salt. So this is what happens when we dissolve particle or matter in the water or in the solution. And dissolution, so I was talking about the hydration actually, so just now I was talking about the hydration. Dissociation, if it is totally separated, if let's say it's not for sodium and chloride, but it is something else, it is totally separated, right? It is totally separated, and that is not in a bonding anymore. So we'll call it dissociation. And lead oxide, yesterday, PB, Oh, this is P, sorry. I'll write it here. Lead oxide or mercury oxide. Mercury oxide we did not provide, but it was in the reference book, lab manual book. So when we did it, we dissolved it. I mean, not dissolved it. We put it into under heat. What happened is lead and oxygen, it separated. It got separated, right? So oxygen was coming out. That makes the glow. So this is how, if we dissolve something in the water and then it gets totally dissociated, that is not in binding anymore. So that will be dissociation reaction. And dissociation reactions is if these things are in a crystal structure. For example, is this sodium chloride is also in crystal structure, or salt. Sugar, these are also crystal structure they provide. So if they dissolve in the water and ionic crystal breaks up, what happens is for sodium chloride is here it is the ionic crystal, so they are not solid in the salt anymore. Whatever we can touch, the salt, table salt, before we put in the water, we can touch, we can feel the hardness of it, but in the water they are not the hard anymore, they dissociate. So this is the dissolution, the crystal structure breaks up. And depends on the chemical identity, these properties, the solute turns the solution different way. All right, so some are non-electrolyte, some are very strong electrolyte, and some are medium. For example, those are ionic bonding, or those produces polar covalent bonding. They will be electrolyte solution. Although the more the ionic strength, right? The more the ionic strength, they will have more electrolyte. There will be more strong electrolytes. For sodium chloride, example of sodium chloride. Sodium chloride is the ionic bond, right, between them, because then electronegativity is more than 2. So it is a ionic bond, or more than 1.9. So it is an ionic bond. So it will produce a strong electrolyte solution. But those who are not that much ionic bond but polar covalent bond, they will also produce some weak electrolyte in this. And those are pure electrolytes, pure covalent bond, they do not have the tension between, they do not ionize the water as well, so they do not carry or conduct the electricity. Water, pure water, in its original sense, I mean in original state, is a very weak electrolyte. Is a very weak electrolyte, pure water. But don't try at home, okay? Do not touch it unless it is shown to you in the lab. Do not touch it because you will have sweat on your body, and sweat is salt, or maybe the water is not clean or pure, so it will conduct the electricity. But theoretically, water, when it is very pure state, it does not conduct electricity. So to make it conductive and to conduct the electricity, we have to add some electrolyte in it so that it becomes electroconductive. Some of the examples of electrolytes are here. Strong electrolytes, you can relate those things. They have more ionic bonding, ionic compounds between them. They have ionic bonding. They have a more tension between them. Weak electrolytes, they have very polar covalent bonding between them, or very weak electrolyte, the tension between them. This one, CH3COOH, I'm sure that you know this is a acetic acid in it, right? This acetic acid, why I'm talking about it, because later on we will be talking a lot about it. This is an acetic acid, and this acetic acid, since it's an acid, it dissociates in the water and it produces a hydrogen ion, right? Since this produces a hydrogen ion, of course it should have another negative ion on it. So this is the acetate ion, and hydrogen ion is produced. But the thing is, why it is weak is they do not dissociate a small fraction, okay? maybe 1-2% of the acid will be dissociated in the water. So that is why they are a weak electrolyte. Non-electrolyte, you'll see that they have the difference between them, the electronegativity difference between the atoms they are bonded to is very similar. So they are very less polar solution compounds, and that is why they do not get dissolved in the water or produce the water more ionic in that sense. Why electrolyte? So this is what I was talking. And for example, it says that predict and explain which of the following system are electrically conducting: solid sodium chloride, molten sodium chloride, and aqueous solution of sodium chloride. We already have talked this, that the aqueous solution of sodium chloride, it will conduct the electricity. Molten one, it will always also conduct a little bit of it, but solid it does not. So in the table salt, if it's a solid form, it will not. But if you try at home, maybe it will, because the sodium chloride, it hygroscopic, it absorbs the water from moisture. So it is not your home one is not the lab grade. It is not a purely solid. It all still have some water in it from the air or atmosphere. So if you try at home, it will conduct the electricity. Be careful, don't do it at home. Now we move to the reaction in aqueous solution. So in chemistry, or in all biological reaction, of course, in our body, that is happening in the water or aqueous solution, mostly or water, in water medium, because in our body or in any other biological thing, they do not have, they are not occurring in the gaseous phase, right, or solid phase. In our body, there are more than 70% of water anyway. So when the reaction is occurring in our body in water phase or solution phase, it is the ions are involved in it. In a way or another, the ions are involved in this type of solution, that is reaction that is occurring. Okay, so when this reaction occurs in aqueous medium, three types of outputs that we can see. That either it will be a precipitation reaction, when there is a precipitation occurs that we have seen in the lab. Acid-base reaction, that will be neutralized. Okay, that will be neutralized. That both of the solution will be neutralized at some point, and there will be no acid or base. Or anyway, so it will be neutralized. So pH will be around 7. And oxidation reduction reaction, either of the compound that is included or involved in the reaction will be oxidized and another will be reduced. So when we are saying about the oxidation and reduction, I mean oxidized and reduced, that is one thing that we will have to consider it, and we are going there actually eventually after later of this lecture. So these three ways the reaction can occur, or three ways the reaction can be identified or quantified to some extent, especially for precipitation reaction. When we add two different type of chemicals, both of them are liquid, right? Both of them are liquid or in aqueous phase. But when they add it together, they will produce some precipitation. In this way, we can see that cadmium sulfide, lead sulfide, nickel hydroxide, aluminum hydroxide. So these type of solid will be precipitated out of that solution, I mean, liquid phase. This is the liquid phase. Previously, when before they were added, both of them were in solution phase. Both of them were just like water or liquid. But when we added them together, they produce solid. Why it is producing the solid actually? What is the problem? This is solubility constant, that something we'll have to remember, I mean consider. We will consider this later on, but for the time being, it says that this is how we we say, I mean, we quantify or identify this is a precipitation reaction or not. And there is laws or some formula what will be precipitated out of what, but there is no hard and fast rule, of course, because chemistry all about exception, right? So now the solubility, when we are saying the precipitation is happening, that means something is precipitating out of the solution which was dissolved in the water. So how do we understand dissolving or solubility? That means more than 1 gram in 100 gram is soluble. That is soluble. We already say that is very soluble, like salt in water or sugar in water. Alcohol in water, ethanol in water is infinitely soluble. How much you put doesn't matter, it will be soluble always. And salt, it is very much soluble. I forgot exactly how much, but it's very much. I mean, lots of salt you can dissolve in 100 milliliter. More than 100 gram of salt you can dissolve. So this is a solubility, but slightly soluble is 0.1 to 1 gram of that compound will be dissolved in water. So it is, we call it slightly soluble, but insoluble is less than 1% will be dissolved in the water or in the solution. Okay, so this is the rule that we were talking about in the last lab when we were doing the chemical investigation of chemical reactions. By the way, so now we are studying the chemical reactions, and we have done this lab already. And I'm sure that you are trying to prepare the lab report, and you are doing good, I hope. So when we relate, the idea is that you will learn more, or you will reflect more on it. By that, simultaneously you are doing the experiment and you are studying the reactions. So I hope that it will help you to understand or relate the things more and to do the discussion in deeper. Okay, so now this table is given in the lab manual, and there is another table which has been given which is very detailed, what of the compound will be dissolved in water or not. So for this table, it says that soluble compound, insoluble compound, and soluble, so insoluble, it is, of course, it is in water. All these things are considered in water, soluble, no, not in water. So basically, all these alkali metal, alkali earth metal mostly are soluble. Okay, alkali metal means this lithium, sodium, potassium, rubidium, cesium, francium. All those things are soluble in water. All the compounds containing these are soluble. Whatever the salt are, this, I mean, of this alkali metal will be soluble in water. As well, nitrate, ammonia, acetate, bicarbonate, chlorate, chloride, perchlorate. So halides, chlorine, bromine, iodine also. So sodium chloride, sodium bromide, sodium iodide, all those things, sodium sulfate, all those things will be soluble in water. But there is an exception, right? Chemistry. So there are silver, mercury, lead. When there is the halides of silver, mercury, and lead, they will be not soluble. If there is a silver chloride, silver bromide, silver iodide, or mercury chloride, mercury iodide, lead chloride, lead iodide, it will not be soluble. It will be precipitated out from the solution. Although all halides of those will be soluble, but only these metals, it is not soluble. Sulfate, all the sulfates are soluble, sodium sulfate, potassium sulfate, calcium sulfate, but not sorry, calcium is exception. So, but what else? Potassium sulfate, all those sulfates are soluble, but silver, calcium, strontium, beryllium, mercury, lead. So if we just remember silver, mercury, lead, these three are always everywhere. You see, silver, mercury, and lead. Only here it is the exception for this case increases to calcium, strontium, and beryllium. So beryllium chloride, beryllium sulfate, beryllium chloride is soluble though. Beryllium chloride is soluble, but beryllium sulfate is not soluble. So this is quite interesting thing. And there is another thing is the insoluble compound is considered that carbonate, phosphate, chromate, sulfide, hydroxide, these all are insoluble. All right. So hydroxide, again, we know that sodium hydroxide, potassium hydroxide, calcium, those are soluble, right? So this is an exception for again with this. But anyway, you do not have to memorize this table or those things, but if you can, it is better, it is easier for you to justify the things. So when we prepare the lab report, we will have a look at it, we'll try to relate, and we'll find out what is happening where. So if we, actually this is already you have, now there is no need to do this. So silver sulfate is insoluble because there is silver here is there. Calcium carbonate is insoluble because this is carbonate of calcium, right? This is an exception in the previous table. Sodium phosphate is soluble because phosphate of sodium is added here, so it is soluble always. Copper sulfide, sulfides are insoluble, that has been indicated in the table. Calcium hydroxide insoluble because of hydroxyl molecule, ions that is attached to calcium. Okay, but potassium hydroxide is soluble. Zinc nitrate, it should be soluble because there is no barrier, and zinc and nitrate both are soluble in there. Okay, so since we know that which is soluble, which is not soluble, and it depends on the ions as well, so that molecular and ionic equations we can prepare. Molecular equations we already have seen before, that all the molecules involved in the reaction that we consider, and the reaction, and the product is forming. So all the molecules are considered here. Ionic reactions, though, only it is considered the ions. Okay, and when it is soluble and not soluble, that we have seen before, ions will be only involved in the soluble phase. So this is important. Ion will be only involved in the soluble phase. That means when there is aqueous, aqueous phase is given, that is the ionic solution. It will not involve liquid though. Liquid means they are in liquid phase, but not necessarily dissociated into ions. Only when they are in aqueous, they will be in ionic form. Like potassium hydroxide, we will see it in a bit. Potassium hydroxide, when it is in ionic form, so we know that potassium is positive, hydroxyl is negative, so in ionic form. But potassium hydroxide, if it is a solid, we will say it is no, we cannot write this positive and negative anymore because they are not dissociated into ions, or when they are in liquid molten state, sodium chloride or potassium chloride, so they will not be written in these ions. Okay, spectator ions, after the reaction is occur, some of the ions, they do not change any involved in the reaction, or they do not change the ionic state or anything, so they will be spectator ions. They are just watcher, they are not taking participation in the reaction. They are still in aqueous form. They were previously in aqueous form. After the reaction occurred, they are also in the aqueous form. So they are the spectator ions. And if you can, if you have time, or if you want, you can just go and to this link and see how the silver nitrate is mixed with potassium dichromate, what is happening. Silver nitrate is liquid that we have seen yesterday, last Monday in the lab. Silver nitrate, when it mixed with some kind of chlorine, silver chloride will be produced. But other reaction also can occur, like silver nitrate when they are mixed with potassium dichromate. Silver nitrate is brackish, a little bit gray, darkish, not dark, how do I say that? It is clear, but it is not transparent. Okay, it's a little dark color. Potassium dichromate is bright yellowish color, and when they produce this silver chromate, it will be a very reddish ruby red type of color. Okay, ruby, a reddish ruby type color. Just go to this link and click on the link, and you can watch the video on YouTube. So what happens is when these two are reacting together, right? When the two is reacting together, silver chromate is produced. Silver chromate is produced, and from this is physical state of that product, we understand this is a solid or precipitation. This is a precipitation occurring. But from here we see this is aqueous. That means silver potassium nitrate in liquid form. Silver nitrate in aqueous form, potassium dichromate in aqueous form, right? And then potassium nitrate in aqueous form as well. So how do we write this is a molecular equation. This is nothing wrong with this. It is nicely balanced and everything okay. So this is a molecular equation, but we want to see which of the species, which of the things that actually did the reaction or actually involved in the reaction, and what state or what charges they carried forward to form this compound. We have to write the molecular ionic equation. So from here, this is aqueous form. Of course, it will be divided into these ions. So silver ion and nitrate ions and potassium dichromate. So potassium and chromate ion. This is also in aqueous form, but you see this is a solid, right? This is solid, so it is not shown as ion here. It is one solid compound. It is not dissociated in ions. But for potassium nitrate, it is in aqueous medium, in aqueous form, so they are also shown as ions. So at the end of the reaction, we understand that silver and this chromate ion, they actually came together. They broke up with these two things, and then they came together and form silver ion. They form the silver chromate. This is the bright ruby color powder. But this nitrate ion, here it is one negative charge, and then this is in aqueous form. This is, and the same thing, it is not doing anything. It is on the both sides. It is just staying at the same way. Potassium and potassium in the same way. So these two will be cancelled out. So this is the ionic reaction we wrote and cancelled out, and then this will be the net ionic reaction. After we cancel these two out, this will be the net ionic reaction. So this involves here potassium, silver and chromate and silver dichromate. This is the net ionic reactions. Example says that predict what will happen when potassium phosphate solution is mixed with a calcium nitrate solution. So both of them are in aqueous medium, right? Both of them are in aqueous medium, and potassium potassium phosphate is mixed with calcium nitrate. So what will happen is calcium will be replaced by this potassium, and this is a double replacement if you want to say. Okay, potassium will be replaced by this, will replace the calcium, and then potassium nitrate will form, but calcium will come close to phosphate ion and then they will form calcium phosphate. Calcium phosphate and potassium nitrate is being produced. Both of them from ionic to, since it is calcium, right? It's involved calcium. If we look at the table, just now we showed before. So if we look at the table, you say the calcium phosphate ion of calcium is precipitated, will be precipitating. It is solid. It does not get dissolved in the aqueous medium. So they are solid, and that is how we see that they are formed in this way, the solid. And as well, potassium, what is it? Potassium and nitrate are not doing anything. They are just here as they were in the liquid form, aqueous reactant form. So they are the spectator ions as well. Barium chloride, aqueous solution of barium chloride and lithium sulfate are mixed and late. So I'm not going very detailed into it. I'll go to the oxidation reduction reaction soon. So barium chloride and lithium sulfate, barium, all barium chlorides are what is that? Soluble, right? Barium chlorides are soluble. Lithium sulfate is also soluble. That we see from the table. We looked at that lithium, potassium, sodium, all of them are soluble, right? So they are strong electrolytes and each dissociate completely in water to give solution. Barium will be formed with sulfate, barium sulfate, and lithium chloride will be formed in this way, this double displacement reaction. But barium sulfate is non-soluble, so it will be non-soluble, and non-soluble salt will be occurred. And the good thing about the barium sulfate is it is so less soluble, so less soluble that it does not get dissolved onto our body or our tissues or wherever. I mean, if we even touch it, it does not get, our skin does not dissolve, take it. So this is less soluble, and that is why barium sulfate, but barium chloride is toxic. The problem is barium chloride is toxic, and barium iodide is toxic. All those halogen of barium is other salt of barium are toxic, but barium sulfate is quite safe. So what happens when we need to do the X-ray or to investigate whether there is a puncture in our intestine or anything? The barium sulfate, this milky shaky, this solution will be, I mean, not solution, this solid will be dissolved in our, will be swallowed, and then we can see from the X-ray if there is any leakage. Lead acetate, whether lead will form an acetate. Yes, lead and acetate is a solid, a liquid. Okay, lead acetate is a liquid and it is soluble in water. But when we add this iodine with this solution, it will potassium iodide, for example, it will produce lead iodide, which will be solid as well. Okay, so lead iodide is, where is it? Okay, so lead iodide, in this way, it is solid. So lead, potassium iodide is added to the lead acetate, and lead iodide is formed, and potassium acetate is aqueous, so it is dissolved in the water. Now, since we understand that some of the chemicals will produce precipitation, and precipitation means that there is solid formation in the solution, that solid is standing out or precipitating out of the solution, right? So if we take out the precipitation and dry it, and then later we make sure there is no water, we dry it, we make it a fine powder, and then we weigh it, right? Mass, take the mass or weight of the compound that has been formed. From there, we can do some investigation or get some idea of what could be the identity of the solution of the chemicals that was involved in the reactions. So this is the quantitative analysis. So quantitative means finding the quantity, right? Quantity is always with the value. So it will be, quantitative means it is always with value, and value means it is always with number. So there will be some calculation and the numbers will be involved in this quantitative analysis. And to determine this, the quantitative analysis, to do quantitative analysis, we have to do some gravimetric or volumetric analysis. What is the gravimetric and volumetric analysis? This gravimetric is we dissolve those compound first, we make the precipitation, we take the precipitation out, exactly what I was discussing. We take the precipitation out and then dry it, then weigh it and try to find out what will be the total volume or total mass of these unknown chemicals. All right. So if by the gravimetric analysis, one example is says that in ionic compound which has in a chloride ion, right, and an unknown metal is dissolved in water, are treated with excess of silver nitrate. Silver nitrate, excess AgNO3, that is silver nitrate, was used to precipitate out all the chlorine is there. Why excess? We have in a compound, in a sample, right, ionic compound containing chloride. Let's say it is a potassium chloride. We do not know, it can be sodium chloride or it can be potassium chloride. In this gram of sample, this potassium or sodium or magnesium chloride is there, and silver nitrate is used to precipitate this chlorine out from here. So why excess? That means if we add enough, we do not know how much will be enough. So let's say that 0.5 gram, 0.56 gram of sample, we add 10 milliliter, right? Even though it's 0.56 gram, but we add excess amount so that no chlorine will be left behind, everything will come out. So this is how the silver chloride will be formed, and we have seen the silver chloride will form a white precipitate from the lab as well. This is the question is saying that if 1.08082 gram of silver chloride precipitate forms, this is 1.0882 gram, right, of silver chloride was formed. What is the percentage by mass of chlorine in the original compound? Percentage by mass of chlorine in original. So percentage by mass, if we want to know the percentage, I have to know the percent of chlorine there first, isn't it? Percent of chlorine there, only then I will find the percentage by mass of chlorine. So percent of chlorine in silver chloride, generally in silver chloride is 24%, because silver chloride molecular weight is 143 and chlorine is 35.45 or 35.5. So percent of chlorine or chloride in silver chloride is 24.72%. So percentage chlorine in the mass of sample, if I have this amount of sample in the chlorine in the sample, will be like this amount, 0.2427. This is the percent of mass. And if we want to know the mass of chlorine, this is already, we have got the answer here, but if we want to know the mass of chlorine, we have to multiply with this mass of silver chloride that was produced. So this silver chloride mass and the mass of chlorine in that is giving us the percent of chlorine is giving the mass of chlorine for us. Another example for here is a longer one. It says that arsenic is because of its arsenic is a very poisonous element or metal and is carcinogenic. So that is why it's poisonous to a human being. So it's poisonous, very much poisonous to the small animals like rodents or rats or something. So for pest control, sometimes this arsenic is used for poison. Okay, so arsenate ion is formed, which forms an insoluble silver arsenite salt. All right. So if we look at it, we'll see that. Okay, we'll come there later. But here we see that arsenite, in silver arsenite, there are only one arsenite. 3 silver though, but only one arsenite is there, right? Okay, this is one clue. And the question is asking that suppose you are asked to address the purity of a technical grade sodium arsenate, the active ingredient in a pesticide used against termite, you dissolve 10 gram of sample in water, oxidize it to something to produce the arsenate and dilute it with water to a final volume 500 milliliter, whatever. You then add excess silver nitrate. Okay, silver nitrate to produce it silver arsenite, because silver arsenite will be solid, right? Silver arsenite will be solid, so that's why silver arsenite was used, and also to give us a good idea of what the reaction is happening, how much the reaction is happening. And after we put the silver arsenite, the PPT produced was having 3.24 gram of the salt. The PPT that's produced. The PPT means silver arsenite salt, right? Silver arsenite salt is the PPT. Now, if we have 3.24 gram of silver arsenite from that 10 gram of sample, right, after the reaction, what is the percentage by mass of sodium arsenite in the original sample? Now, one thing can be confusing, that this arsenite and then arsenate is different symbol. But from here, if we look at the reaction later, we look at the reaction here, that silver arsenate and sodium arsenate and sodium arsenite and silver arsenate, they are actually from 1:1 reaction. They are producing 1:1 reaction. That means if it is sodium here, it will produce 1 sodium ion as well. Let's say in that way. Okay, so it will produce one. So from sodium arsenite, 1 silver arsenite can be produced. That is the simple thing. So they have, although they have different symbol, but they can be easily solved in this way. So yeah, not much time, yeah. So silver and arsenate is produced. 3.2 gram of the silver arsenate was produced, right, by reacting of that with excess of silver nitrate. Silver arsenate was produced, and we find the number of moles, because always number of moles are important. The silver arsenate, the number of moles is 7.005 times 10 power negative third. Moles of silver arsenate was produced, and the number of moles of silver arsenate is equal to the number of mole of silver. The arsenate ion is equal to the number of moles of silver arsenate, because it is 1:1 a reaction, right? This is 1 and it is producing 1. So if it is X amount of silver arsenite there will be X amount, sorry, if there was a X amount or X mole of arsenate ion, there will be X amount or X mole of silver arsenate as well. All right. Okay. So this is the silver arsenate. And from here we see that number of moles we find from the silver arsenate, and another reaction, sodium arsenite, since this is the sodium arsenite from here as well is the same number of moles of sodium arsenite will be produced. The number of moles are remaining same because the number of moles, as I said, that's the arsenate 1 and here is 1. Right, because when we are adding water, it is producing sodium arsenate from sodium arsenite. When we are adding water, it producing silver arsenite, AgAs. Okay, so silver arsenite producing. The number of moles remaining same. So the same number of mole that we found can be used to find out the mass of sodium arsenite. We just multiply with the number gram per mole of sodium arsenite, and we find this is the 0.91 gram of sodium arsenite was in the sample, and it is only 9.1%. Another way you can do it by going through a hard way, it is the easiest way. You can go and you can find the 3.2 gram of arsenite, sodium arsenite produced, how many moles of this, and same way but in detailed form. So this is formed silver arsenite, and it is in 10 gram of it. So what is the reaction occurring for sodium arsenite to silver arsenite, and the same way in a detailed way you can write it. So both ways should be okay. Now we go to oxidation and reduction reaction, although we don't have time, but I just want to start it today. We have already seen before oxidation is oil and rig. Oxidation is losing of electron. Reduction is gaining of electrons. So those who are losing the electrons become oxidized. Those who are gaining the electron become reduced. And those who are helping it to lose electron, not losing, okay, helping it to lose electron, that will be oxidizing agent. That means a reductant will be a good oxidizing agent. And those who are helping it to gain electron, that means the oxidizer, will be a good reducer as well. So before next meeting, we will have our next class, of course, on next Wednesday, Monday, Tuesday. So I will do this thing, finish first, and then I will go for acid and base. But before we go to acid and base, please make yourself comfortable with oxidation, reduction, all right? Oxidizing agent, reducing agent, oxidizing agent. Okay, if you can write my writing, and a reducing agent. Reducing agent, oxidizer, and reducer, the same thing actually. So these two things, please be comfortable with this. Oxidation is losing the electron. So if any element, let's say A, is easy to lose electron and it becomes positively charged and becomes an electron, of course it is losing an electron, right? So we have to show the electron as well. So it is oxidation is happening to A. For a B, if it takes an electron and becomes negatively charged, B negative, let's say it becomes B negative, right? So this means it is reduced. So oxidation and reduction, in this way we can that whichever is losing the electron become oxidized, whichever taking the electron is getting reduction. So there is a very hard way to remember that losing of, but oil and rig, if you remember this, please remember this, oxidation is losing oil, oxidation is losing, of course, losing of electrons, and reduction is gaining, of course, gaining of electrons. So this is today. I will see you on next Monday. Of course, I will be online for half an hour to discuss about the lab and the project that has been given to you. And another thing is, oh, I wanted to mention that, guys, please take the survey, okay, that has been on for 1 week already, for almost 1 week. So please take the survey. You are safe. You will not know. I mean, we will not know who is who. We will not know your name. It is totally unanimous. But what we can do is we can improve. How can we improve the things that can, I mean, the teaching or what you want more, we can do more. So this is it. Please, so everybody, I can see 20 of us is here, or 23 students are here. So please take the survey and fill it by today. Don't wait, please. Okay. So thank you very much. I'll see you on Monday, the lab session at the same time for discussion of the lab and the project.